So one is this, that you define it in a very concrete but messy manner. So E comma V is P comma E theta. By this I mean the UI is xi not equal to 0. Gij, I believe I wrote it, there's a typographical error in the one that I wrote. It's xj over xi, not xi over xj, on u alpha intersect. What this means is, you're taking a disjoint union, meaning you're taking a collection of u alpha cross c's, a disjoint collection. Okay? Ideally, actually, they're all, suppose this is CPN, they all intersect. Let's say this is, it's not like this, the picture is different, but let's pretend it's like this, say it's U1, U2 and U3. But I'm first taking a disjoint collection and I'm identifying this part with this part, this part with this part, and these lines by means of linear transformations. G1 naught, G2, and so on. Okay? This is what I'm doing. I'm literally forcing, I'm taking a bunch of, you should think of these as, if you take a comb and the bristles of a comb, and I'm literally forcing them and gluing them together by means of these transition functions. Yeah? And I gave you an exercise where I asked you to prove that it's indeed a complex manifold. I mean, I won't do it in detail, but it's not rocket science, because if you take this open set here, I mean, this is already, you can see, suppose you divide it in, this is already a coordinate open set, and so you take this, and the coordinates are these ones and the ones here. More generally, this may not be a coordinate open set, but that's okay. You can divide it into small coordinate open sets, and you have coordinates here and coordinates here. That's roughly the idea. It's not very hard. Just have to be a little nitpicky, that's all. Okay? In general, you can define the line bundles this way by means of these transition functions, and they, of course, satisfy these two very important properties. Okay? Another way is a more geometric one. You first define O minus 1, which is the dual. So you define this as the dual of this, where this is defined to be a subset of Cpn cross Cn plus 1, satisfying, so what is Cpn? It consists of these homogeneous coordinates and a vector, and V is required to lie on this line, if you so will. Okay? And this is the dual of it, namely, every fiber of this is a linear functional on this, meaning it takes a vector from here and spits out a number. So for example, if I take a homogeneous polynomial like this, I can think of this as a section of O1 in two ways. One way comes from here, you can directly do it. Another is, this takes in a vector V and simply spits out this quantity. Okay? This is what it does. Okay, so there are two ways of looking at O1. Both of them are profitable. This is the one which is more natural in my opinion. This one allows you to prove that every holomorphic section indeed comes from a homogeneous polynomial. Okay? And as I said, this is the deep underlying fact that connects algebraic geometry and analytic geometry in CPN. So any questions from the last time before we move on? Okay. All right. Okay, by the way, just to give away the suspense, I told you a non-existence result. Most tori are not projective. Here's an existence result, if you wish. All compact Riemann surfaces, meaning complex manifolds of dimension 1, are projective. Okay. So all Riemann surfaces can be studied using algebraic geometry, if you will. That's the implication of this. The ones that are projective are called abelian varieties, if you give it a little more data. Right.
So in particular, all complex 2 tori are projective.
Complex 1 tori.
1 tori, sorry.
Okay, so the next order of business is this. So how to potentially come up with an embedding of a given compact complex manifold into some projective space. Let's see some way by which we can try to do this. We will fail in some cases, but is there any way to do it in the first place, right? I mean, at least in the case of usual manifolds into Rn, you had this trick with partition of unity. You already had coordinates, a local part was inside Rn, you just globalize it using partitions of unity. You don't have that trick available here. So what can we do? Okay. All right.
Here, when you say the Riemann surfaces are projective, how does the Riemann metric behave with the complex structure?
So metric in the sense that, so how do you come up with a Riemann surface? One way is if you have a metric on a usual surface, a conformal class defines a Riemann surface. So yes, in a sense, the Fubini-Study metric induces a conformal class. But other than that, you can't say much more. Okay, so how does one come up with an embedding? So what does this mean? Suppose I manage to come up with a map from here to here. What would that mean? That would mean, given a point P, I will get something like this. I mean, ideally, if these were functions, then I would simply be asking for a bunch of n plus 1 holomorphic functions. That doesn't make sense. They're all constant if they were functions. But I'm just saying, if these were functions to complex numbers, I would be asking for a bunch of them, right? So already you can see you need lots of functions or whatever correct object that might be, right? But these are not functions. These are to be thought of as sections of O1. Correct? You have O1 here. And this is the pullback of O. In other words, we need lots of sections of a holomorphic line bundle that is supposed to resemble this, whatever this means. Already we can see, how do you come up with an embedding? Well, let's reverse this process. Suppose you have a holomorphic line bundle over this. Suppose it has lots of sections. Then potentially you can pretend, well, take a bunch of them. Right? Hopefully this sort of a process, if it makes sense, should give you a map to CPM. That's the rough idea. Let's make this more precise as we go along. Okay? So the first order of business is the following. On a compact complex manifold M with a holomorphic line bundle, the vector space of holomorphic sections, maybe I'll write it as a theorem, of holomorphic sections is finite dimension. This is actually a very non-trivial result. Notice that, to give you an analogy, if you take smooth functions on a smooth manifold, this vector space is infinite dimensional, right? Holomorphic functions on a compact complex manifold is one dimensional, it's just constants. Holomorphic sections of a line bundle is still finite dimensional. Okay? And this is not easy to prove. If you wish, one way to mumble some words to convince yourself is that when is a section holomorphic? When it satisfies a PDE, whatever this means. You don't know what this means yet. What the hell does this mean when it is a section? But let's pretend you do. It satisfies a certain PDE, right? PDE of this sort are very special. They are known as elliptic PDE. And elliptic PDE in certain situations have finite dimensional kernels. That's the essential thing. But anyway, forget the proof, but the point is, this is a very important, so a lot of work in many situations would go into finding what is the dimension of this space. There is no formula that will give you the dimension, but there is a formula that links this to the dimension of some other space, called the Riemann-Roch formula. Okay? If you want to deal with it, the dimension is, you can't exactly get a formula, but at least sometimes you can get an estimate using the Riemann-Roch formula. It's a special case of the Atiyah-Singer index theorem. Okay, so the bottom line is n plus 1 is the dimension of holomorphic sections of L. Okay, so I'm using, and these guys are all bases, they form a basis. So my strategy is the following. You give me a holomorphic line bundle on a compact complex manifold. I'll look at a basis of the sections, which is finite in number, right? And I will construct this map. What does this even mean, right? A section is a function to some manifold. So what does this even mean? What this means is the following. Locally, on say some u alpha in N, L restricted to u alpha is a trivial bundle. In other words, locally you can pretend that all of these on u alpha, you can pretend that these are all holomorphic functions. on U alpha. On U beta, there will be different holomorphic functions. They will not be the same holomorphic function. They will be different, but they will be related according to the transition functions. I hope this part is clear. Locally, by definition of a line bundle, locally it is trivial. In other words, locally it looks like this. So a section is simply a holomorphic function. But if you choose a different open set, you get a different holomorphic function, and these two are related by means of the transition function. So what this means is actually you take a bunch of complex numbers and you create this object. You identify them if they differ by this map is well defined. What that means is it does not depend on the trivialization. Does not depend on alpha. Indeed, if we choose beta on U beta, this would have been S0 beta of P, S1 beta of P, and so on. But these two are related, right? This is S0 beta times G alpha beta, S1 beta times G alpha beta, and so on. So the G alpha beta pulls out. Remember, what do we mean by putting these colon signs? When all of them differ by the same complex number, you can pull it out, as long as it's non-zero, right? So this is a well-defined map. Not well-defined, but at least it makes sense as of now. Yeah.
Shouldn't we choose a section such that it doesn't vanish?
Yes, you're right. Good point.
One under one.
Sure. This formally makes sense. At least it does not depend on the alpha. It could potentially be a well-defined map. But there are still problems with it. Namely, what if all of these are zero? What if the line bundle is such that, for example, there could be no sections? If you take this thing, this has no non-zero sections. So you couldn't have constructed this map had you been given this line bundle, right? So you need sufficiently many sections. In particular, you at least need this to be well defined. For this to make sense, for the map defined to make sense, at every point P, there exists some I so that SI of P is not zero. If all of them are zero, what does that even mean, right? And if this is supposed to represent a line passing through the origin, if you just, so it doesn't make sense when all of them become zero, right? So so this is at least one necessary requirement. You must have at least as many sections so that this happens, right? So in particular, you could not have used this guy in place of this. If we were looking at CPN itself, this would have been a wrong choice. Okay. The next order of business is to hope that this is an embedding, as in this should be one-to-one and its derivative should be injective, right? So already we can see that the obstruction is finding a line bundle that has enough number of sections for this to make sense, namely at every point one section at least should not vanish, and this should be one-to-one, and the derivative should be injective. So the obstruction is find line bundles, this is the slogan, with many sections. As I keep repeating, this is the main obstruction. How many sections? Well, so that all of these are satisfied, right? Now, one can say that, all right, one has identified one criterion. I mean, I can just say that the Coderre embedding theorem is if there exists a line bundle so that this map is an embedding, you're done. But that is not good enough, right? I need to be able to come up with a better criterion, right? I want a differential geometric criterion. Maybe you may not have heard these words before, but something to the effect of if this line bundle has a metric with a certain kind of curvature property, then you should be done. That is the criterion I'm aiming towards. You might also ask, how will you verify that? How can you make sure that you have a line bundle with such a curvature property? That's a different ball game altogether. Okay. Yeah.
So even when you do all this, you only made sure that locally it is injective, right? You want to get an embedding.
Yeah, I'm saying, firstly, I hope it's clear that this map is a well-defined thing, it's a global thing. It does not depend on the trivialization. Why? If you change trivialization, you get the same thing. Okay, so this map is well-defined. Now you can ask whether this map is globally injective or, I'm not saying that I have proven this map is so. I'm requiring that to be the case, okay? But I hope that it is clear that this map itself makes sense, okay? I am defining this map using local quantities, but if you change your local data, this map still gives you the same answer. Okay? Okay. So why do I need the sections to be in this setting? If they were linearly dependent, I think you can find a point where this becomes 0. Perhaps. That's the problem. Okay. Okay, so just to keep our aims in mind, just let me write it down once. One, there should be enough sections, number of sections, holomorphic sections, so that the first requirement is at every point P, S of P, there exists a section S, which is some linear combination of a basis, such that S of P is non-zero. If there exists one section such that S of P is non-zero, clearly one of the SIs should be non-zero, right? That's good enough. Second thing is we want it to be one-to-one. Namely, suppose P and Q are 2 points in M, then there should exist at least one section S such that S of P is not equal to S of Q. This is informally written as sections separate points. Okay, they separate points. You have a section that distinguishes them, right? And the derivative should be injective. This is a more painful thing to write. Okay, so this is what we want to be able to do. So let's erase everything. Where's that? Sorry?
What do you mean
S of Q?
section? S of P lies in the
Well, if you wish, abstractly there's a map to a manifold, right? So these 2 points should not go to the same point on the manifold.
I mean, SFP license is fiber on the.
See, S of P, what does this mean? So it lies up, sure, it's,
We need a section which vanishes at P and does not vanish at Q or something like that.
okay, fair enough. What I meant is that. You're right. Maybe, okay, I'll write it this way. The reason why I wrote that, I agree that doesn't make sense, thanks, but the reason why I wrote that is because at the end of the day we will do much more than this. Our method of proof will do the following. You give me any 2 vectors you choose at 2 points, I will produce a section that takes one vector here and the other vector there. That sense. Right. Okay, so let me state Coderre's theorem. Of course, you don't know many of the words in this theorem, but let us state it. Before we go ahead and define these terms, right? A compact, complex manifold M can be embedded into CPN if and only if there exists a holomorphic line bundle L admitting a metric whose churn connection has strictly positive curvature. Okay. Such L are called ample. In fact, given such an L, there exists a K large enough so that L raised to K over M gives the embedding. Sn of P is the embedding where this is a basis for, I'll use a seemingly perverse piece of notation here. This means holomorphic sections of L raised to K. Okay, H not M comma a line bundle means holomorphic sections of that. Why am I using that weird piece of notation? If you learn sheaf cohomology, you will know, but we won't do it. Okay. So this is just some fancy notation. So this is saying that if you have such bundles, by the way, L raised to K is called very ample. Okay. So if you have an ample bundle, namely one that has a metric whose curvature is positive, then a large power of it can be used to produce the Coderre embedding. So what do these terms mean? What does this, so we need to know the meaning of these terms first, and then we need to see how one goes about trying to prove such a theorem, right?
But how is doing it tensor?
Tensor. Oh, sorry. Yes, you're absolutely right. What I mean by this is this. I didn't want to erase this. Okay. Okay. So, as I said, this criterion itself seems a little unfair because it's asking you to produce a line, to check if there's a line bundle which has a metric that has certain properties and so on. How would you check these things, right? Fortunately, although we will not go into this, just for future reference, there is this thing called Lefschetz's theorem on 1-1 forms, whatever these words mean. This is usually very helpful in deciding such things. Since we are using big words anyway, this is a special proven case of the Hodge conjecture. Okay. This is a very useful theorem. It was known for a long time, and this is useful in producing line bundles that have those properties. In fact, it is using this sort of a result that you can prove all Riemann surfaces are. For Riemann surfaces, it's much easier, but you can prove that you can find a nice criterion that will tell you when your complex torus is projective or not. Just given the lattice, you can decide that. There is a criterion like the lattice vectors should satisfy, if you take their matrix, they should satisfy one equality and one inequality. So if you need to satisfy an equality, it's very rare, right? If you take a random lattice, it's not going to satisfy some equality. It might satisfy an inequality. That is why most of tori are not projective. Okay. Anyway, so So what we will do is, after defining these terms, the strategy of the proof will be reducing it to a PDE, which I'll give an idea as to how to solve. This is not the usual proof, by the way. It's the proof given in this book, Griffiths and Harris. Uses some more algebraic geometry. In particular, it uses something called a blow-up. The proof I'm referring to is, my friend George Marilyn tells me it's due to Donaldson. So I think it's there in one of his books. Nonetheless, I believe this proof is far more important than the algebra-geometric proof, because a proof akin to this was, if you jazz it up a lot, it was used recently in the sense of a couple of years ago, by Donaldson, Chen, and Sun to prove a very important conjecture, the Yao-Tian-Donaldson conjecture. So it's much more useful to know the proof I'm going to talk about than the algebra-geometric one. All right, so maybe I should give some more references since people have asked me. As I said, Griffiths and Harris, it has a wealth of information, but it's quite difficult to follow. A slightly better book is by Hoyt Rex. The advantage with this book is, in addition to being better in terms of exposition than Griffiths and Harris. It has some exercises as well. So you can look at Hoybrex. And if you like metrics, Riemannian geometry and the like, there's a book by Tian. I think it's called Canonical Metrics in Kähler Geometry or some such thing. It's a green colored book, so it's fondly known as the green book. And if you're interested in metrics a little bit more, there is one by Sekaletidi. Yeah, these two are for metrics. For people interested on the algebraic side of things, this is a little more algebraic geometry. Donaldson would also, his notes, I think they're there on his webpage. And one more important reference is Demai's book, which covers some algebraic geometry and some aspects of several complex variables, which also play a role in this story. So these are the references. I would suggest you start with Hoybrex if you want to start somewhere. I mean, Demai is free, it's there on his webpage. This guy has notes on his webpage, which then became a book. The other three have to be downloaded illegally. So anyway, so let's give some preliminaries. Let me define this thing called the so-called holomorphic tangent bundle. I am assuming that you guys know what the usual tangent bundle on a manifold is. Do people know this? Who doesn't know this? Raise their hands. All right, fine. So, the point is that if you take a manifold, so M is a complex manifold of complex dimension n, so real dimension 2n. Okay? Right. So, if you take the real tangent bundle, the usual tangent bundle, this consists of, if you at every point P, you have a tangent space, right? A real tangent space, if you will, which just consists of tangent vectors. This consists of basically tangent vectors. So it's 2n real dimensional. Akin to that, you have the complex. So locally, these TPMs are spanned by the following basis, right? By d dx1, d dy1, d dx2. There's a reason I'm writing coordinates this way, okay? So locally they're spanned by these. Akin to that, akin to this construction, T10M, the so-called holomorphic tangent bundle, is locally spanned by these things. Okay, I'm writing superscripts now. D, dz3 and so on. Recall that d dz is half d dx minus d dy. Okay? So that's what the holomorphic tangent bundle is spanned by locally. In other words, the 1, 0 is there to indicate that these are actually these, as opposed to their bar versions, which would be T01n. And that's not a, you don't probably know what a vector bundle is, but it's not going to be a holomorphic vector bundle, it's going to be anti-holomorphic. As you can imagine, whatever these words might mean, right? You have a bar over there. So in other words, if V is a tangent vector, then V is locally Vi ddxi, okay, where Vi's are real numbers, right? Now if you change coordinates, to Wi, to, let's say, maybe I'm going to be using, let's for now forget using these things. If you change coordinates to, let's say, yj, then this is some wi ddy, and there is a transformation rule. This is j dyi dxj vj. The point of writing this is just to say that the tangent bundle, whatever it is, if you write a vector field, if you write locally in coordinates, you change your coordinates, it transforms according to a certain rule. This is some change of basis. This is a matrix multiplied by this vector. Recall that we had a similar situation for line bundles, right? We had a transition function. So taking Q, let's define vector bundles. If time permits, I'll do them in detail later on, or Sushmita will do these things. So, vector bundles. A smooth vector bundle of rank R on a smooth manifold, let's call this X to distinguish it from complex setting, is defined as follows: the disjoint union of U alpha cross R R G alpha beta, which is a matrix this time, R cross R, the vector, where U alpha are open sets and G alpha betas, these matrices, are invertible matrix valued smooth functions satisfying the co-cycle conditions. This is a vector bundle. It's a direct generalization of the line bundle to higher rank, to higher dimensional vector spaces, right? So the tangent bundle is an example of a vector bundle where the transition functions are given by these, right? The holomorphic tangent bundle is an example of a holomorphic vector bundle. What does that mean? This is going to be a complex vector space. This is also going to be complex, and these will be holomorphic functions, holomorphic matrix valued functions. Okay? All right. So, likewise, for holomorphic bundles, for holomorphic vector bundles on complex manifolds. Complex manifolds. Okay? Right. Here's an exercise just akin to the line bundle case that you can do. So, it will help you understand vector bundles much better. So prove that a smooth vector bundle of rank R satisfies the following properties. It is a smooth manifold vector bundle V, manifold of real, of course, since this is smooth, I'm just going to say dimension. It has a projection map pi such that for every p in X, pi inverse p is a vector space vector space of dimension r around every p in x, there exists a neighborhood, an open set UP, such that pi inverse of UP is diffeomorphic by means of some diffeomorphism phi to UP cross RR, with phi preserving the fibers and being linear on them. Okay. So this property is called local triviality. Prove that any smooth manifold V satisfying the above is isomorphic in this sense to a vector bundle. Okay. So perhaps that's the usual definition you're accustomed to if you've seen vector bundles earlier. But for the purposes of differential geometry, this is somewhat more useful. You just construct quantities locally and just check whether they transform correctly or not. That's the idea. Okay. Likewise, just maybe I'll write it here itself. So if S from x to v is a smooth function satisfying pi composed S of p is p, then it is called a smooth section. A smooth section. Just like in the case of line bundles. Okay. All right. So akin to line bundles, one can define V star, the dual, by means of transition functions is G alpha beta inverse transpose. For line bundles, there's no transpose because you just have one number, right? It's 1 cross 1 matrix. If you have V tensor W, then this is the so-called Kronecker product of matrices, meaning that this is G alpha beta 1 1 times H alpha beta, G alpha beta 1 2 H alpha beta, and so on. Suppose this is rank R and this is rank S. This is an RS cross RS matrix. It's a standard operation in linear algebra, the Kronecker product of matrices. And you have the pullback, etc. Okay. So, just like line bundles, you can do all these operations for vector bundles, and you have one more operation, the direct sum, which is just a block diagonal matrix. Right? Yeah, let's see if time permits. We'll do that in detail later, or at least Sushmita will do these things. But we need a little bit of this to proceed for what is going to come. And the same kind of thing works for holomorphic bundles. Huh? There's nothing. All of these things, if you replace the word with holomorphic, it still works. These definitions make sense. What's the point of defining all this? All right. So T10x M is an example of a holomorphic vector bundle, T01 is not an example of a holomorphic vector bundle. If you wish, it is an example of an anti-holomorphic, whatever that. I leave that to you to figure out. It doesn't matter, whatever it is. The point here is the dual of T10 is sometimes written as omega 10. This is the bundle, the holomorphic bundle of 1-0 differential forms. What does this mean? That means locally, a smooth section looks like some Fi dzi. Okay? So remember we had differential forms in Cn and Rn. This is just the global version of it. A differential form on a manifold is simply locally a differential form in Rn which transforms correctly under change of coordinates. So that's the slogan. On manifolds, whatever you do in Rn or Cn can be done, except when you change coordinates, it should transform correctly. That's the way physicists look at these things. Okay. Likewise, we have omega pq, which is not holomorphic, of course, which is a smooth bundle of pq forms. What does that mean? Locally, a section would look like Fi1, I2, Ip, J1, Jq, dzi1, dzi2, dzip, dz bar, J1, dz bar, Jq. Okay? I mean, if this is the first time you're seeing differential forms, this can be a little tricky. But if that is the case, please feel free to come to me after this lecture. But this is not rocket science. As I'm saying, it's just your usual differential forms. If you're familiar with them, at least in Rn, it's just a jazzed up version where you have z's and z bars. I mean, it's what you would expect when you have complex numbers. Right? You'll have z and z bars. Because Shubhajoy would need this terminology, if your manifold is of dimension n, this is a holomorphic bundle consisting of things that look like this. Some locally there's no sum, it's just dz1, dz2, dzn. This is sometimes written as km and is called by algebraic geometers as the canonical bundle. Curvature might require this. It's just terminology for, this is the maximum kind of dimension for these, right? You don't have any more dz's to play around, that's the point. And it's a holomorphic one, there are no bars in the equations. Okay. More definitions. Just as we have the exterior derivative d, suppose on smooth manifolds, that is, suppose omega is some fi dxi, then d omega is dfi dxi, which is sum of I and j, dxj dxi. Remember? So you get a d takes a 1 form and spits out a 2 form and so on. And d square is 0. Just like we have in Rn, but on manifolds. Akin to that, as we have mentioned earlier, and I'll do so once again. I know this is boring stuff, it's a lot of definitions, but unfortunately it's necessary to set up. This language is necessary for what we will do in a moment. Similarly, on a complex manifold M, you have del and del bar, d equals del plus del bar. If you have omega being, let's say, fi dzi, for example, let's say omega is fij dzi wedge dzj bar. Suppose it's a 1-1 form. Del omega gives you a 2-1 form. ijk del bar omega gives you a 1-2 form. I hope this is clear. I mean, this is exactly what we did on Cn and Rn. We are just carrying this out on manifolds globally. So you just need to write them down in local coordinates with the understanding if you change coordinates, it transforms in a particular manner. Right. There is, however, one subtle definition. Usually definitions are not subtle, but I want to call this a subtle definition. And this is absent in the case of smooth manifolds, and that is as follows. Suppose V is a holomorphic vector bundle. Oh, sorry, this is N. We are calling complex manifolds N, right? The definition is as follows. Suppose S is a smooth, not necessarily holomorphic, section of this holomorphic bundle, or V. Okay? So, in a local trivialization, S can be thought of as a vector full of functions. S alpha is a vector full of functions. It's a rank R vector bundle, complex holomorphic rank R vector bundle. That is, locally it looks like U cross CR. Okay? So you have R complex valued functions. And the subtle definition is this. You can make sense of this object. How can you potentially try to define it? You take a local representative of this, as in, what do I mean by this thing? I mean the following. S1 alpha dz bar I dz bar I, S2 alpha dz bar I, and so on. This is a vector full of 0, 1 forms. This is, locally you can define whatever the heck you want, but the point is it should be a globally defined object, meaning it should transform correctly when you change coordinates. Okay? In other words, if I choose a different trivialization, what will I get? Is this well defined as a global object? Is del bar S as defined above independent of alpha? That's the only disadvantage with defining things locally, in that you have to keep checking this. If you do it globally, you don't have to, but it's most natural to do these things locally anyway, right? What does this mean? Suppose on U beta, we would have defined this like this. S2 beta and so on, right? In other words, is it a section of V tensor 0, 1 forms? These are sometimes called, in Kähler geometry, vector valued 0, 1 forms, even by physicists. Meaning, so what does this mean? Let's actually look at this. So what's the difference between this and this? You're replacing an alpha with a beta. Let's erase this for the moment. What is Si alpha? What is S alpha? It is G alpha beta, a matrix. It's an R cross R matrix of holomorphic functions, invertible matrix of holomorphic functions times S beta. So del bar S alpha is del bar of G alpha beta times the vector S beta, which is, I'll be a little pedantic because this is the first time. It's just the Leibniz rule. And this is of course 0, and you'll have G alpha beta times del bar S beta, which is exactly the way it is supposed to transform. If you take this, these things are supposed to transform that way. If you take a vector valued 0, 1 form and you change your trivialization, the new guy is related to the old guy by simply, what's that? G alpha beta times the old differential form. Old form, new form. Okay. And what is making all this magic work? It is the fact that this is 0. Otherwise, you would have had a nasty term sitting here, right? So in other words, this makes sense only for holomorphic vector bundles. You try playing the same game for smooth vector bundles and try to define ds for a section S. Then you will encounter a term like dg alpha beta, which is a nasty term you don't want, right? So that is the problem. So this is a very subtle definition in that it works only for holomorphic vector bundles. Okay. Why is this a useful definition? Can anyone guess as to where this sort of a thing can be useful? What's the point of making this definition? Yeah, so when do you say a smooth section is holomorphic? When this is 0. This is a globally defined quantity. When this is 0, only then can you say a smooth section is holomorphic. So we have globally formulated holomorphicity as a partial differential equation. That is the point of making this definition. Okay? So a smooth section is holomorphic if and only if del bar S is 0. Globally. Okay? By the way, usually partial differential equations are equations for sections of vector bundles. Because otherwise, how do you add quantities? If you have d square f dx square plus d square f dy square is 0, what are you adding if you can only add on vector spaces? Right? I mean, okay, I'll be a little more cautious. You can formulate them in other situations, but they're usually for vector bundles. Well, emboldened by our success, we could try doing the same thing for del, right? But we'll be in trouble. If you try to define del S as del S1 alpha, del S2 alpha, and so on, then what will happen is del S alpha is del of G alpha beta S beta, which is del G alpha beta S beta, plus a good term. This is not 0.
Why
Yes.
is del bar as 0 if it is a holomorphic section?
If it is a holomorphic section, so what would be a holomorphic section? One whose local representatives are all holomorphic functions. Right? When is the local representative of a holomorphic function? When del bar of each of these is 0. Right? Right? So yeah, if you try to play the same game for del, you fail miserably because of this derivative term. But there is a very nice way to correct it, and that forces a definition upon us. There is a way to rectify this situation. So we are forced to define this object called a connection. Let's look at line bundles for now. Smooth line bundles. Let's call these L tilde just to remind ourselves that they are not necessarily holomorphic, just for psychology. So let's look at these. We want to define, the aim is to define a quantity like this, which is locally this, but this is not good enough, plus something else. Okay? Such that this should be a section of one forms Tx star tensor the line bundle. These are vector value 1 forms. Okay. There's something else will be added to cancel this part out. Okay. But before we go ahead and do it, let's pause for a moment as to why we would care about doing such a thing. So in Rn, forget about manifolds for the moment. If I give you a function f, what is the point of doing this? What can we do with df? Df is a one form, it's just simply the collection of partial derivatives. Well, derivatives tell you how things change, right? And when you first encounter derivatives in multivariable calculus, you don't encounter differentiability in its full glory, right? You first define directional derivatives. Directional derivative of a function is basically the derivative of the function in that direction, right? Which is, in terms of this one form, what is it? It's df acting on this vector field, right? So, we want to do calculus with sections, right? We want to know what it means for a section to be constant. Why would we care about finding constant sections? Because we can choose that quote-unquote constant to be whatever we want, right? Those kinds of things. So we would want to define a directional derivative. And that is the point of this. You see, I'm saying it's a section of the cotangent bundle and this, meaning it is supposed to take in a vector field and spit out a section, right? This takes a section and spits out a section, which is the directional derivative of S along X. This is the aim here. That's the point of defining this weird differential operator. Okay? Now there's something else here. Should be linear in S. Okay? In what sense? Well, what properties do we want here? Firstly, if you add two directions, you better require this, right? It should be linear in this, for sure. And what else would you require? If you multiply S with a function, well, you should be able to use the Leibniz rule. These are the most obvious properties you would demand of the directional derivative, right? So this is a differential operator that satisfies these properties. This nabla is called a connection. The whole problem with manifolds and vector bundles is there is no unique way of taking directional derivatives. There are lots of ways of doing it. That's why it's called a connection as opposed to the connection. So locally, what should a connection look like? I claim a connection should look like this, where exercise. So I put this here. We are dealing only with line bundles, mind you, but this story makes sense for general vector bundles. Okay? Exercise. Okay. Locally, prove that a connection nabla on a smooth line bundle L tilde over X satisfies nabla S alpha is D S alpha plus A alpha S alpha, where A alpha is a one form that obeys this rule. A alpha is A beta minus D logarithm of G alpha, which is for vector bundles that won't make sense. In other words, the directional derivative is what you would define naively, just ds, plus a correction term. The correction term is simply a one form multiplied with s, transforms in a rather strange manner. Okay. So a connection is the data of certain one forms A alpha that transform in a strange manner. That's what a connection is. For a line bundle, and likewise for a vector bundle. So how do you come up with connections? How do you prove connections exist on any line bundle? There is a partition of unity argument to do it. You construct them locally and patch them up together. We won't do that. Instead, what we will do is something slightly better. On a holomorphic line bundle, L over N, there is a nice way of getting connections. I believe this was first discovered by Chern. So the idea is the following. Before we go ahead and do this, we need to know what a metric on a, we will come back to this. This is our goal. We need to know what a metric, a smooth metric on a smooth line bundle L. So what's this? So what is a metric after all? A metric tells you a way to measure distances and angles, right? So you have a vector space at every point. I want to measure how long the vector is at every point. So what would I have to do? I mean, I would want to measure the length. We denote a metric usually by h. We want to measure this quantity. Somehow we want to make sense of this. Well, at every point, I would want to define it like this, where this is a smooth positive function. At every point, how do I measure the length of a vector? Take the usual Euclidean length and multiply it by a number, right? Scale it up. And if this has to be independent of the trivialization, this better be equal to s beta squared times h beta, which means h beta should be mod g alpha beta squared h alpha. Sorry. Yeah. So this is a metric is simply on a line bundle is simply a collection of positive functions, real valued of course, transforming according to this rule as so. Okay? This is a Hermitian metric because we are dealing with a complex vector space. You can define, for real vector bundles also you can define metrics of course. now we have this very nice form way of constructing a connection. Given a Hermitian metric H on L over N, define A alpha according to this formula. So what does this mean? Let's pause to see what I'm talking about. What is a connection? A connection is given by the data of a one form. Remember, it's a correction term added to the most naive thing you can think of. That one form is locally defined and it transforms in a certain manner when you change your trivialization. Okay? Now I claim if you give me a metric on a holomorphic line bundle, there is a very nice way to define a connection by means of this formula. For starters, is this a connection in the first place? What does this even mean, right? Is this a connection? In other words, is A alpha equal to A beta minus D ln G alpha beta? This is what we have to check. So let's do so. What is A beta? A beta is del ln H beta. So A alpha minus A beta is del ln H alpha over H beta, which is this quantity minus D ln mod G alpha beta squared. And what's this equal to? This should ideally be this, right? Why is this the case? Firstly, you seem to have a square there. Where is the square going away? You just seem to have one thing here. Two. Excellent. So firstly, what's this? This is del ln G alpha beta bar, which is del ln G alpha beta plus del ln G alpha beta bar. So, what's the problem with that?
That will be scalar.
So, why is this 0?
Because d omega bar by dz is also the uniformity is holomorphic.
See, when is a function holomorphic? When del zi of this is 0, which means del zi of G alpha beta bar is 0. A function is holomorphic if and only if f bar is anti-holomorphic, if you so will, right? So this is del ln G alpha beta. We are still not done, right? It better be D. But I claim this is del plus del bar ln G alpha beta because this guy is 0. Okay? So once again, this makes sense only for holomorphic line bundles. There is no canonical way of defining a connection given a metric on a smooth line bundle. Okay? So it's remarkable that Chern came up with this formula. I mean, it seems very random, right? I mean, but notice one very curious thing about it. This is a 1-0 form. There is no 0-1 piece to it. So I don't know how Chern came up with this connection. I don't know if he wrote down this local formula. That seems a little too random. But there is a more geometric meaning to this. It has to do with the fact that there is no, you can define this globally by requiring that there better be no 0, 1 P's and one more condition, which I will leave to you as an exercise now. Okay, stop. Once I keep this. So here's an exercise. Verify that the Chern connection is compatible with the metric. What does that mean? That's what I'm going to say. With the metric, that is D of ST, the inner product, is nabla ST plus S nabla T. Just stop here.
So, can the Levi-Civita on smoke manifold be also interpreted as directional derivative of the Riemann metric based on this? I mean, can one
Yeah, all connections are directional derivatives.
of the Riemann metric? Can one interpret the Levi-Civita?
Oh, this in this framework.
Yeah, yeah.
Not quite, but you can, for Kähler manifolds, these two are the same.
Sure,
But
sure.
no, not quite.
But because, I mean, somehow or the other, there's this torsion-free condition which is very mysterious and non-geometric. If
So
it can be interpreted this way,
No. So torsion freeness comes from its analog in the curve situation, right? When you say a curve is torsion free, it sort of lies in one plane. So,
yeah.
or physicists would say that there's no rotation. There's a way to make this precise in terms of angular momentum. But, yeah. For me, by the way, the point here as an analyst is you need to be able to find coordinates where the metric is standard up to the first order. That would force torsion freeness.
Yeah. Yeah, I mean, del 2 del x del y is del 2 del y del x.
Basically, that's the thing.
Repeat again, it doesn't recognize the answer.
Let's start with another exercise, or maybe I can do that. Should I start with the exercise? Rather, the last time I gave a couple of exercises, I believe, did people do them? Did people have questions? I mean, last time as in the last, I mean yesterday. Is there any questions regarding them? Right, let me ramp up the difficulty of my exercises considering they're too trivial. Here's one. It's not too difficult or anything, but was a little bit. It's actually on M. Oh, by the way, so my notes will be posted on Tejas's webpage because I can't access mine from here. What's your webpage?
So IISER Pune का /tilde Tejas.
Right. So please look at Tejas's webpage.
Maybe it's maths.IISER.
Right. Right. So assume L restricted to U is locally.
Before you start, just may I request something?
Yeah.
Since the lectures are being recorded,
Right.
Since Tejas is maintaining a page with these links, then one can have a resource there for.
Sure.
Okay.
So I'll put this up at lunchtime. It's not up yet.
Okay. Sure.
Yeah.
So suppose this is locally trivial. That is, every section S can be on U can be identified with a function with a every holomorphic section with a holomorphic function S alpha. Okay? Prove the following. We can find a holomorphic section S alpha on U such that mod S H square at P is 1. So what ramification will this have? If I find a holomorphic section S on an open set so that at a particular point its magnitude square is 1, the point of doing this is, so if T is another section, then mod T square is T over S alpha as complex magnitudes of complex numbers. Okay. In other words, that is, if we change the trivialization to the one given by S, in other words, T is some lambda times S, then mod T square is exactly mod lambda square. This is just a complex number. So it's just the Euclidean metric in this new trivialization at that point, at this point. Okay? So you're making the metric at a particular point standard, just the Euclidean metric. Actually, prove that in one, we can make sure that the derivative is 0. In other words, the metric in this new trivialization, is equal to 1 up to the first order. The corrections are on the Taylor expansion has 1 plus 0 plus higher order terms around P. Okay. Deduce that the Chern connection in this new trivialization equals 0 only at the point P. So what is the point of this exercise? The point is, you can always pretend that if you are given a holomorphic vector bundle and a metric and the corresponding churn connection, that at any given point you can pretend that the metric, that the connection is 0 at that point. And this pretense is very useful because whenever you take derivatives of metrics, whenever you have a first derivative of the metric, in these coordinates it is 0 at that point, only at that point. The second derivative won't be, but the first derivative is. So that's a useful thing to have, right? Sometimes, by the way, maybe I won't use that terminology. Yeah. Things are called normal coordinates in case of manifolds. Alright, coming back to what we were discussing earlier, remember that if you have a line bundle, what is a connection? A connection is locally D plus A alpha, where these are one forms that are supposed to transform this stuff, right? This is a particularly unpleasant transformation rule. But there is an obvious thing you can do here that constructs a global object out of it. What can you do? This is a collection of one forms that don't agree, right? Take D on both sides. This is 0. So this gives you a global object, right? This is denoted by theta. Some people, maybe Sushmita will denote it by F, maybe. dA alpha is a global 2 form called the curvature of nav. Why is it called the curvature? How is it measuring anything that has to do with curvatures? That is a debatable thing. If X was, let's say for the sake of argument, a Riemann surface, okay, and L is its holomorphic tangent bundle, which is a rank 1 complex. It's a line bundle. And if that A was of a very specific type, if you know what a Levi-Civita connection is, then this curvature would actually measure the Gaussian curvature, how curved it is. Like you take two curves, measure, put this Riemann surface, put the surface in R3 or R4 or wherever you can put it, and you take curves through the point, measure their curvature, their radius of curvature, and multiply the maximum and minimum. That's what you get, okay, for that particular connection. So by analogy, we call it the curvature. Right. So for the Chern connection, what is the curvature? The curvature is D. A, what is A? A is del ln H, which is del plus del bar ln H. So that's del square, which is 0, plus del bar del ln H. So it's a particularly nice formula, del bar del ln H, for the Chern connection. Okay. By the way, what happens, maybe, an exercise that we will do now, what happens if you change the connection to the curvature? You change the connection. Maybe I'll call it theta of nav just to indicate it's the curvature of that connection. What do you think is going to happen if you change this? it's surely going to change. It's not going to be invariant. But well, what does it mean to change the connection? Suppose you, this is locally, let's say this is A2 alpha, maybe, A1 alpha. What is A2 alpha minus A1 alpha? Let's call this small a sub alpha. Can you notice something about the small a sub alpha? Is there anything noteworthy about this? So one form sure, one u alpha. What more? Okay, what happens when you change your trivialization? When you change alpha to beta? What happens to the small a alpha? How does it change? Well, let's see how it changes. What's this? It's A2 beta minus d lng alpha beta. This is A2 alpha minus d lng alpha beta. So this is equal to A beta. These things cancel out, right? In other words, the bottom line is the difference between two connections is a globally defined one form for line bundles. For line bundles. So you can get all possible connections for your line bundle by just choosing one single one and keep adding one forms to it. So what ramifications does this have on the curvature? So theta of nabla 2 is dA2, which is dA1 plus dA. Nabla 1 plus dA. In other words, when you change your connection, the curvature changes by an exact form. So what is the point of that? What that means is if sigma is a surface inside X, the integral of this over this is the integral of this plus this, but by Stokes' theorem, this is 0. Because whenever I say surface, I mean without boundary. So the integral of the curvature along every surface is independent of the connection chosen. It's dependent only on the vector bundle. It's an invariant of the vector bundle. If you're familiar with Theorem cohomology, the Theorem cohomology class is an invariant of the vector bundle. If not, it's just the integral of every surface. Okay? So these integrals, they're collectively called the first, conventionally you put this here. As of now you see no good reason, but there is a good reason. These integrals are called the first Chern class, or the cohomology class if you're familiar with it, C1. Okay. they're all integers, by the way. The integrals. It's not obvious they should be integers, but you should be, if you've done any bit of geometry on surfaces, this should remind you of the Gauss-Bonnet theorem, which is the integral of the curvature is 2 pi times the Euler characteristic. That's where the 2 pi comes in. The square root of -1 comes in because you want it to be real. Okay? Okay, so finally, so remember the Coderre embedding theorem says that if you have a holomorphic line bundle which has a metric whose Chern connection has positive curvature, then the manifold is indeed projective. So we have defined all the terms there, holomorphic line bundle, metric, Chern connection. We have not yet defined what this is. So what could that mean? Curvature is something like this, right? It's a 1-1 form, it's a 2 form if you so will. What could it mean to be positive? How can a 2 form be, a 1-1 form be positive? What's a reasonable way to define this? So this is locally some theta I j bar dzi dzj bar, where these are functions, right? Sum over I. This is actually a matrix, not a. This is a matrix, right? In fact, this quantity, this is a Hermitian matrix. Exercise. It's very straightforward to do it, but it's a Hermitian matrix. So now we know what it means to be positive, right? This matrix better be positive definite, right? Means that theta ij bar is positive definite. And this condition does not depend on what coordinates you choose. Check that exercise, check that this condition is independent of coordinates. Or coordinates. Okay? So now we at least know quote unquote the statement of the Coderre embedding theorem. What it is saying is, if you have a holomorphic line bundle which has a metric such that this particular 2 form, when written in local coordinates, comes from positive definite matrices, then that line bundle, then that particular manifold is projected. So it seems like a random theorem, right? I mean, how do you come up with metrics such that this seemingly random 2 form is positive? It's not at all straightforward, right? So how does one do these things? So that is not clear yet, but at least now we know what the statement is of the Coderre embedding theorem. Okay? Alright, so now that we know what the statement of the Coderre embedding theorem is, there is a very pleasant, if you have a metric whose churn, if you have a line bundle with a metric whose churn connection has positive curvature, namely these things are positive definite matrices, there's a very pleasant thing that happens. That is the following, that if you take the exercise, prove that if L equipped with this metric over N is positively curved, that is, this is positive definite, where this is equal to del bar del ln h. Then theta ij bar defines a Hermitian metric on T10x. That is theta ij bar. I'm choosing a different convention, so I'll write. Should I write that? Okay, I'll do this. Y z is z dagger h theta. Y is well defined, where y and z are complex tangent vectors. Vectors lying in the span of ddz1, ddz2, and so on. So what this is saying is, so what does it mean to have a metric on a vector bundle, on the tangent bundle, which means that you can measure the lengths of tangent vectors, right? My point is that this particular thing is giving you a positive definite matrix of the correct size. It's an n cross n matrix. So naively you can think that maybe this can function as a metric on the tangent bundle, and indeed that is correct. Okay?
Curiosity. If the curvature is not positive definite but just degenerate, non-degenerate,
you get a symplectic form. If it's not degenerate.
Even for a symplectic form, we need positive definite.
Sorry?
Even for a symplectic form, we need positive definite.
Not quite. A symplectic form just is closed and non-degenerate.
I guess it won't be compatible. J won't be compatible.
J won't be compatible, you're right. No, but potentially J can still be compatible and it need not be positive definite. That is called a tamed symplectic form, what you're talking about. If
J won't be tame, I said.
yeah, it won't tame it.
Yeah.
Okay. So this is, once again, I agree that I'm giving all of these as exercises, but whatever you naively think will happen is going to happen. You have a matrix of the correct size, it's going to define a metric, that's all. It's not rocket science. Suppose L dual is the dual of L over N, okay? First of all, L dual has a natural metric. What is it? If I give you a way to measure distances along a vector space, on its dual there's an obvious metric. On a one-dimensional vector space, what should it be? It's simply 1 over h. H dual, h tilde, is simply 1 over h. Right? That's the obvious metric. If you scale a vector by 5, you're scaling the corresponding covector by 1/5. Right. So, what is its curvature? So, the curvature of L dual is del bar del ln 1 over h, which is minus del bar del ln h, which is del bar ln h. Recall that del bar is minus del bar del. Why? Because d square is 0, del square is 0, and del bar square is 0. And d equals del plus del bar. So just square on both sides. Okay? Right. What's more generally, if you take L raised to k, meaning L tensor itself L times, let me, L raised to k has a natural metric, which is simply h raised to k. Okay? The curvature of L raised to k is del bar del ln h alpha raised to k, which is k times the curvature of L. So what is the point of saying all this? If you have a metric whose curvature is positive, meaning that this particular matrix is positive definite, you take L raised to k, you suddenly have a metric on it whose curvature can be made as large as you want. That is the point. You can make it, you can ramp up that k to be 1 billion and you'll get hugely positive curvature. Okay? That is the point. So this can be huge by taking a large tensor power. They're not, no? One is h and one is 1 over h. Oh yes, yeah, you're right. I mean, you're smoothly, if you, that's how you get a smooth as smooth. Yeah. Okay, so here's a remark. While I'm saying it's a remark, it's actually an extremely important point. Given any Hermitian metric, let me call it capital H, just to tell H on T10N. I'm calling it capital H just to tell you that it's a metric on the tangent bundle, not on a line bundle. This 2 form I comma j is well defined as a 2 form. What does it mean? It means that if I change my coordinates, I get the same thing back. Okay. New coordinates. Basically, it's a globally defined 2 form. Not just any old 2 form, it's a 1-1 form. My conventions have been chosen so that maybe this is bar, I think. I have to check this. Anyway, it's not important. The point is, if this 2 form is closed, that is, d omega is 0, this metric is called Kähler. So that is saying L is positively curved is the same thing as saying the curvature of L is a Kähler form. So all I'm saying is, it's just a piece of terminology. The holomorphic tangent bundle is a complex vector bundle. At every point you have a complex vector space. If you put a Hermitian metric on it, meaning at every point you can measure lengths of vectors, then you can form a 2 form out of it, maybe admittedly in an artificial manner like this. If this 2 form is closed, such a metric has a name, it's called a Kähler, and the 2 form is called a Kähler form. So in this language, L is positively curved if the curvature form is a Kähler form. Just language, nothing more. But there is a point to defining this. Why would anyone think of d omega being 0, right? That seems like a very random condition. But it's not that random. This exercise we will do tomorrow for sure, even if you haven't thought about it. But I want you to think about it, so I will give this as an exercise. Move on. Okay. Suppose H is a Hermitian, capital H, is a Hermitian metric on the holomorphic tangent bundle. So I know some of you have not studied Riemannian geometry, but given a manifold and its tangent bundle, I mean you have a vector space at every point, so you can endow it with a Riemannian metric, which is just a way to measure lengths of vectors. The point being, if you have a curve, you can measure the length of the curve, for instance, by calculating the speed and integrating and so on and so forth, right? So given a Hermitian metric on this, prove that H induces an honest Riemannian metric G on the real tangent bundle via an R linear isomorphism between the real tangent bundle and this. Smooth isomorphism. In other words, so as vector spaces, the holomorphic tangent bundle at every point has complex rank n as a vector space. So real rank 2n. The real tangent bundle also has the same rank, and there is an obvious isomorphism between the two. You can write it, but I suggest you think about it. Why would there be an isomorphism between vectors spanned by d dx1, d dy1, d dx2, d dy2 and so on, and vectors spanned by d dz1, d dz2 and so on? I claim there's an obvious map between these two. And using that obvious map, this thing induces a Riemannian metric on the other thing. Okay. Conversely, given a G on TR, there exists a Hermitian metric on this. I mean, of course, if this exercise is true, whatever method you use to prove it should work the other way around, right? You're using an isomorphism to change one to the other. And this is harder. And this requires, I mean, it doesn't require anything special, but it requires a little bit of thought. Prove that H is scalar, that is closed, where omega is this thing, ij, hij, dzi, dzj bar, if and only if there are local complex coordinates zi such that H is the identity matrix up to the second order. In other words, the whole point of defining this seemingly weird condition is that it is equivalent to saying that your metric in certain well-chosen complex coordinates is almost the Euclidean metric up to the second order in Taylor expansion. The error terms are only in the second order. So if you take the derivative of the metric at that point, it is going to be 0 in these coordinates. Why would you want to, what's the point of having a metric almost being Euclidean? Well, most of the things you do can be simplified. Especially if you write a PDE and so on, whenever derivatives of the metric appear, at that point you can set them to 0, which is a useful thing, right, to prove estimates if you're an analyst. This is equivalent to Kähler's. So this is the real point. This is just an offshoot of it.
And the leading thing is the curvature term?
Yeah, this part will be related to curvature. Is the curvature? Yes. Up to certain factors. So these coordinates have a name. They're called normal coordinates. If you have done any Riemannian geometry, you will know that if you take a Riemannian metric, you can choose real coordinates so that the same thing happens. The metric is standard up to the first order, right? They are called normal coordinates there, and the same thing here. Okay. And in fact, if you have done some Riemannian geometry, you would have heard of the so-called Levi-Civita connection, right? That and this are that connection and the Chern connection are exactly the same on a Kähler manifold. That is the point. If you give me a complex manifold with a Hermitian metric, it gives you one connection. There's an obvious connection, the Chern connection. It also gives you a Riemannian metric, so there's a Levi-Civita connection. These two connections are exactly the same precisely when this happens. And how do you prove it? The proof is right here. Because this says that the Riemannian metric is also identity up to the second order. That is exactly the same as saying it's the Levi-Civita connection. Because its first derivatives are all 0 at that point. Prove that, once again, this is for people who know Riemannian geometry, these two. The other two, the others can also attempt it. The Riemannian volume form, if you've seen this is used to measure the volume of the manifold, is omega raised to n over n factorial. Maybe there is a factor of 2. No, there's no factor of 2. Yeah. So there's a very pleasant formula for finding the volume of such a manifold. It's just take omega, raise it to n and integrate it, divided by n factorial. I mean, if it's a Taylor manifold, it's the same as the usual ones. Yeah, in general, this Chern connection on a manifold, it's, I don't know of any meaning. It's perhaps an important question. People study the analogs of Ritchie flow for these things. As of now, I think they're just a way to get NSF grants, but I don't know if they have any deeper consequence. One more remark, and here on a Riemann surface, this should be straightforward. Remark, on a Riemann surface, every metric is Taylor. Why? Excellent. So, Taylor means that some two form has to be closed, but all two forms are closed, right? Sorry?
On the side.
Right, that's what I meant is on a Riemann surface, all two forms are closed. So in other words, all the machinery of complex geometry can be used to study surfaces. If you just give me a surface with genus G, a bunch of a torus with n holes, it has nothing to do with complex analysis per se, right? But it turns out you can treat every surface as a Riemann surface and force the machinery of complex analysis on it. So far we have not done any examples. Here's an explicit example of a metric. Take O minus 1 over the projective space. What is O minus 1 again? It's a certain subset of Cpn cross Cn plus 1. Okay. I claim that this has an obvious metric. What metric can I choose? Recall what is the definition? It's what subset is it? It consists of these things and a vector v such that v points along this direction. So what way can I use to measure the lengths of the one-dimensional vectors on this?
Cn plus 1 is a standard.
Yeah, exactly. The vectors are sitting here, right? There's an obvious metric there. So here's the metric. The definition of the metric is simply whatever, v1 squared plus v2 squared and so on, right? So there's an obvious metric. So it's obviously interesting to calculate its curvature. And one arrives at a very pleasant surprise when one does that. Let me write this down in coordinates. Okay? So, you need to first find a trivialization of this. Suppose you take on u naught, that is x naught is not 0. The coordinates on Cpn are what? It's equal to 1, z1, z2, and so on. Correct? Because this is x1 over x0, this is x0 over x0, and so on. We're just pulling the x0 out. So on this, every vector v is equal to v1 times this basis vector. If you wish, you can think of this as the basis vector. It's a one-dimensional vector space, right? So what is the length of v1? So rather, the length of v1, v is v1 squared times a function h, right? What is this function h? I'm taking u naught, so I'll put an h naught here. the knot comes from this. What is it this? This is simply 1 plus mod z1 square plus mod z2 square plus so on until mod zn square. What is the curvature of this bundle, of this metric? Let's calculate it. So it's just a calculation, but let's do it just to get practice. So what's the meaning of curvature? It's simply del bar del ln of this metric. So it's del bar del of log of z1 squared zn squared. So it is del bar of this times z1 bar dz1, z2 bar dz2 and so on. So that is, sure, this appears to look messy, but it's actually quite a pleasant curvature expression compared to the nonsense you'll usually see.
Z1 bar with Z1.
Oh, sorry, you're right. Minus square times z1 dz1 bar plus z2 dz2 bar plus so on, wedge z1 bar dz1, so on. Okay. So what is this? It is 1 over mod z1 square so on times whole square times 1 plus sigma mod zi square. I'll take a minus out here. J dzi wedge dz j bar minus, or rather plus, this thing z1 zi bar dzi sum over I multiplied with z j dz j bar. This is wedge product. Okay. Looks like a rather messy expression, but here is the punchline. If you look at this, I claim this is scalar. In other words, if you write this matrix down, what is the matrix? It is zi bar zj plus the identity matrix times 1 plus mod zi square. I claim this is positive definite. The reason is if I take j bar, that is vi zi bar sum over I and j, right? Sum over I, vj bar zj sum over j plus vi mod vi square, or rather mod vj square, maybe I'll write mu here, times 1 plus this. I think there has to be a minus sign somewhere. It's this.
Z1 with Z1.
I think it has to be a minus sign. Where is this? So this is minus. Right. So when you compute this, this is greater than 0. That is a straightforward calculation using the Cauchy-Schwarz inequality if you so will, so I'll just leave that. So the bottom line is the curvature of O minus 1 is negative. In other words, the curvature of O1, which is minus of the curvature of O minus 1, is positive. So by what I mumbled on a while ago, that means that this thing defines a metric. You know, this, I forgot the factor, this factor here, if you put it here, this is a metric on the tangent bundle, and it has a name, it's the Fubini-Study metric. It's a very famous metric on CPN, and it comes from a very obvious choice of things, right? It's not very unnatural. There is another way of looking at this Fubini-Study metric. In the first class, as someone mentioned, CPN is also this, right? This thing has an obvious metric on the sphere, and it descends to a metric on CPN, and up to a factor, I think, of 4, these two are the same. Okay. But writing down the curvature of that metric is much harder than writing this down. Usually you have to use some fancy Riemannian geometry like the O'Neill's formula or something, because in coordinates that looks much worse. Okay, so this is a concrete example of a metric on a line bundle giving rise to a Kähler metric. So notice that if M is a submanifold of CPN, the O1 bundle restricts to an O1 bundle here. So this admits a line bundle with positive curvature. So it's a necessary condition. Coderre's embedding theorem goes two ways, right? If you are projective, then you better admit a bundle with positive curvature. Yeah, that is the case. It is the O1 bundle. The other way is the more complicated one. If this happens, if there is a bundle with positive curvature, then what do you do, right? Okay, I hope these calculations are reasonably clear. I mean, in case you're wondering, I've only computed it on this open set, right? Maybe on some other open set I can get negative. I can't. Why? Because this thing is positive definite, strictly positive definite, and it's a continuous function. This covers almost the entire manifold. So on the other places it has to be positive. Can't suddenly go to 0. Okay. So just to recap once again before we go ahead, what we have done is we have defined complex manifolds, we have defined compact ones. Then we saw that one way of producing examples is by taking homogeneous polynomials in CPN. And we decided that maybe not all manifolds can come that way. The Coderre embedding theorem states that if you have an ample line bundle, namely a holomorphic line bundle with a metric whose curvature is positive, what does positive curvature mean? You write that 2 form down, the coefficients should be a positive definite matrix. If that happens, your manifold indeed sits inside CPN. And we know what the map ought to be as well. Just take a bunch of sections and just embed that using those sections, right? And we decided that this map makes sense if 3 conditions are satisfied. At every point, there should be a section that is not 0 over there. if you give me 2 points, the section should separate the 2 points. In other words, you give me 2 vectors, I should be able to find a section that takes on one vector at one point and another vector at another point. The third thing is the derivative has to be injected, which seems like a more complicated condition, but there is a very pleasant way to state that also. Okay? So we need to, the bottom line is, we need to produce line bundles. Given a positive, an ample line bundle, we need to produce lots of sections. So the aim is, given an ample, meaning positively curved line bundle, need to produce lots of holomorphic sections. This is the aim. This is the way, this will prove Coderre's embedding theorem. So the rest of the discussion will be about a sketch of the proof. It's not an easy proof and it requires a lot of PDE theory, so I'll just give a sketch, just to give a rough idea. So we need to produce lots of holomorphic sections so that what of L raised to k, where k can be chosen to be as large as you want, as necessary, so that this is an embedding into CPM. Okay, so this is our aim. Now this looks like a very tall ordeal, right? I mean, forget about sections of bundles and so on. If we wanted to produce functions, we are in trouble because they're all constants, because it's a compact manifold. But say it's not a compact manifold. Say, let's take just CM. How do you produce holomorphic functions with whatever requirements you want? It's not a straightforward problem, right? Even on C, if I want a holomorphic function to satisfy a bunch of requirements, maybe you can use some Weierstrass product or some such explicit way of doing it, right? Maybe. But in general, what can you do? How do you produce holomorphic functions? You can produce smooth functions without any trouble, right? If I did not have this requirement, if it was smooth, say for the sake of argument, I want a smooth section S, given a point, given P, I want a smooth section S such that S of P is not 0. Can you do this? It's very, very straightforward, because near P, there is a neighborhood so that this is just this. You can surely find a smooth function that is not 0 at a point, and let's say that function is f, multiplied by a bump function rho, which is 1 on, this is up, which is 1 here and 0. Right, this is rho, this is P. So you can easily do this job for smooth sections. It's trivial. In fact, you can do not just satisfy this requirement. If you want to separate points, if I give you P and Q and I want you to take two different vectors, well, what do? Just choose a constant section here. Suppose I wanted to take a vector v1, a vector v2 here, and just cut them off. Trivial, right? You can also make sure the derivative is injective, by the way. I'll come to that. So if you want just smooth function sections to do the job, it's trivial to do this. The problem is we want it to be holomorphic. So we can find smooth sections to do whatever we want. The problem is this is not 0. So how do you correct them to make them holomorphic? So what we want to do is to add a correction term so that this is 0, and the correction term should not screw up the other things. Like the correction term at P should be 0, at q it should be 0, for example, if I give you 2 points, right? So the point is, and its derivatives maybe should satisfy some property if you want injectivity to still hold. So what would this mean? The correction term should satisfy this PDE with these kinds of boundary conditions. If you manage to do that, you're done. You can prove the Coderre embedding theorem. So very roughly speaking, we will do it in a little more detail, but we want to solve a PDE with certain weird boundary conditions, namely boundary conditions at 2 points. Normally you solve PDE with a boundary condition on some circle or some such thing, right? Here we have 2 points on a compact manifold. So how the hell does one solve such PDE? That's a challenge, right? So that is the idea. By the way, this method of proof, as I might have mentioned, is thanks to Donaldson, and the main theorem that will come into play is due to Hermander. Okay. Right. So coming back to this thing, remember what were the requirements we had in mind? One, well-definedness. For every point P, so suppose so what we will do, we will do the following. Do this. For every pair of points P and Q in X, we will find a holomorphic section S that obviously depends on which on P and Q, right, with a given first order Taylor expansion with a given specified first order Taylor expansion at P and Q. That is, if we are given two vectors, u1 belonging to the fiber at P, u2 belonging to the fiber at Q, and two tangent vectors and two other vectors, v1 vector belonging to this and v2 vector belonging to this. We will find a global section S such that S of L raised to K for K sufficiently large so that S of P is U1, S of Q is U2, the derivative S at P is V1, the derivative at Q is V2. In very simple English, this is just saying that you give me the section and its derivatives at those 2 points. I will find a holomorphic function section that matches up your data up to the first order. You're specifying the first order Taylor expansion. Why the first order Taylor expansion? Because we need to take care of the derivative being injective, remember? So this is the problem. Solve a PDE with boundary conditions, your function or section or whatever is specified up to first order at 2 points. Now this doesn't look like any PDE you would have ever seen, right? Normally you solve the Laplace equation with some boundary conditions, maybe you can do it explicitly or something. So all those techniques will fail, and there's a very new technique that is needed here. And this technique is so important that it has proven theorems in algebraic geometry that cannot be proven using algebraic geometry, at least not yet.
So this is X is a Riemann surface or
X is sorry. M is any complex map, compact complex map. So, before seeing how to do it or why doing that will prove the Coderre embedding theorem, or maybe actually, let's see how this helps. Suppose we manage to do this. How does this prove Coderre embedding? Once we do that, then we will try to solve this problem. Okay? So, what do we want, by the way, to prove Coderre embedding? We want the map to be well defined, namely, so given a what does well definedness mean? For a given point P, we need a holomorphic section S such that S of P is not zero, correct? Of course that's going to be satisfied. We are doing much better than that. We are specifying first order Taylor expansions no less. So this will be done trivially. Injectivity. If P is not equal to Q, just choose U1 to be different from U2, then S of P is U1, S of Q is U2. And so that's why, I mean, you can choose one of them to be 0, the other one non-zero. So it's injective. This requires a little bit more thought. The derivative of what map? Let's recall, it's P going to this weird thing where this is a basis. Si form a basis is 1-to-1. This requires a little bit more thought, and this is where I claim this thing has to play a role. Okay? So what will we do? So, suppose that for contradiction's sake, suppose this is not so at a point P. What does that mean? You take the derivative of this map at P, it has a kernel, right? So that means, so you, let's to compute the derivative, let's pretend, let's assume without loss of generality that S naught of P is not 0. Okay? So this is, since we are in CPN, this is S naught, S2, and so on, right? Okay. Right. Choose coordinates in M so that P is at the origin. Okay, and choose normal coordinates. what I'm going to do is I'm going to choose my coordinates and trivialization so cleverly that whenever I have to take a derivative of the metric at a point, regardless of whether it's the metric on the bundle or whether it's the metric on the manifold, it will be 0. Okay? So we can pretend that this funny symbol is simply our usual derivative. Just our usual derivative at that point. That's the whole point of choosing these nice coordinates. Now, what does it mean for it to be injective, the derivative? It means this quantity where I goes from 1 to n times Vj is 0, so j goes from 1 to n for all. There exists a v, there exists a vector v so that this happens. Correct? That's the definition of the kernel being non-trivial. There is a v so that applies in the kernel. So, how does that produce a contradiction? So, the point is, we have not used the full strength of what we claim we will do. So choose S to be such that S of p is 0 and the derivative is the vector v times S naught of p, where S naught is this thing. Okay? Right. So how does that help? Let's compute and let's see. So supposedly this is 0, right? S over S naught dzj vj, which means 0, since S is spanned by these things, ds S naught vj, sum over all j, supposedly, right? So let's calculate this. So it's del S at p, all of this is at p. Del S of p, S naught of p, S naught square of p, minus S of p, del S naught of p, times vj, del zj, del zj is apparently 0. So let's see, is
the
this...
squares in the denominator.
Sorry, this is square is denominator. Okay, right. So how does this help? S is S C naught S naught plus sum of C mu S mu for the other ones. So what is this? S naught times sum of, I said it's Ci Si, right? Sum of Ci del Si of p minus S of p is 0, so this term goes away, over S naught square p Vj, which is sum of Ci. We have chosen this to be V times S naught. So the bottom line is you get Vj square, which is 0, right? Is that it? So what's this? Si Zj, not Vj square. This itself so this be this way. let me just do it here. So this is 0. Sorry, that was unnecessary. This is just sum of vi square, which is positive. It's much easier. So it's a contradiction. What I'm saying is, if you're going to find sections with specified 1 jets, you've already found too many sections for this to have a kernel. If you compute the derivative, you'll see that if there is a kernel, there's a contradiction. Okay? So the bottom line here is, it is enough. What we are trying to do there is too strong. We don't need to do that much, but we will end up doing that much. Okay? I mean, there's no real extra effort in making sure this also happens. In fact, there is no real extra effort in making sure that all the derivatives up to, say, the 10th order are also specified. Okay? If you wish, in more fancy language, the R jet can be specified at any point. And not just 2 points, you can choose 25 points and you can still do that. The same technique yields all of this.
Where are you using the curvature though?
That is introducing this holomorphic section. Remember I told you I have to solve a PDE with certain boundary conditions? That's where I need it. Okay? I hope it's clear that doing this is good enough to solve our problem, namely to prove Coderre and Embedding. Actually doing that will be more non-trivial, but okay. It's just a calculation, you just have to do it and you'll see what I'm talking about. So the real question is, we need to solve a PDE with certain weird boundary conditions, right? And there's a very clever way to incorporate the boundary conditions. And that is, I don't know if Donaldson came up with this idea or if Hermander did. I think it was Hermander. Yeah, it was Hermander because he invented it for a problem in several complex variables. So the technique is very beautiful. So the idea is this. So, well, before we go to that technique as to how do you make sure that those boundary conditions come into the picture, here is an exercise which we've almost already solved, except for a small part. Prove that there are smooth, but not necessarily holomorphic. Not necessarily holomorphic. Satisfying global sections S with specified first order Taylor expansions, specified 1 jets if you will, that are actually very well behaved. They are holomorphic no less in small neighborhoods of P and Q. In small neighborhoods, whatever, meaning I can make them as small as I want, that's what I meant. Of P and Q, coordinate neighborhoods no less, P and Q, and supported, meaning there's 0 outside on slightly larger neighborhoods. I know I'm not being precise, but intentionally so. The precision just obscures what I'm trying to say. It's easy to make this statement rigorous. Even the proof is not rocket science, it's very straightforward. Meaning that given P and Q, I want to be able to find a section which specified Taylor expansion that's 0 outside, and in a slightly smaller neighborhood, it's holomorphic. I want to find smooth sections doing this job. Yeah, we've already almost done that earlier, except for the first order Taylor expansion part.
then finally it's going to be a t-bar equation on the complement.
No, on the entire thing. With the boundary condition being the correction terms should not screw up the Taylor expansions. That's the point. So, okay, before winding up, let me just recall what Mahan was just saying now. So, what we want to do, our strategy is, suppose, let's call this section S tilde. Suppose we are given that our section S is S tilde plus a correction. Del bar of the correction is equal to minus del bar of S tilde, which we will call eta. Okay? We'll call the correction term T from now on. Okay? And the correction term has 0 is at near P is 0 plus order mod z squared, where z equals 0 is P, and say at W, where W equals 0 is Q. This is what we want to do. If we do this, we are done, right? So this, we want to solve this particular PDE with these boundary conditions. So the first step would be to translate these boundary conditions in a way that is amenable to analysis, and then to solve it. And to solve the PDE is where we need the curvature to be positive. And I'll show you why you would need such a condition. Okay?